hopefully today we will finish this chapter. And it has been a long time, so let's remember it together. So we have been talking about galaxies and dark matter. And we also talked about what happens when galaxies collide, okay, when they merge. This is what happens in the evolution of galaxies. And we were talking about how there are some possible ways that in modern astronomy we think about galaxy formation from the beginning and evolution. We covered these three, you don't see it, of course. We covered basically these three topics up to now. And today we will continue with black holes in galaxies and the universe on the large scales. Yes, and when I finish these two topics, I will end the lecture. I will not go through the new chapter, okay? Our new chapter is a very interesting one. Actually, it will be about cosmology. So we will start that on Thursday, okay? So just since it seems that we will have some extra time today, I want to go through what we have been discussing about this chapter. Okay, these are some just very important points here. So as you may remember, when we were talking about the Milky Way galaxy, this was the first time we actually saw a rotation curve like this. Okay, and a rotation curve is just the rotation speed of a, for example, it can be a gas cloud, molecular gas cloud, or a star, or something like that in the disk of the galaxy. Okay, it's the speed versus the distance from the center. Okay, and we can have such a measurement in spiral galaxies actually, because they have the disks. So it makes sense that we can follow something in distance in the disk of the galaxy. Okay, this was kind of an important observation because it showed us very groundbreaking result in our understanding of the universe actually, because it showed us that the speed of the gas clouds or stars or whatever there is in the disk, it doesn't follow the Keplerian orbits. Okay, and I mean the Keplerian orbits, the physics about it is something that we are sure about. Okay, we are sure that Newton physics is okay. Otherwise we cannot study universe. It makes sense, yes? Okay. So the theory is okay, the maths is okay, everything is okay, but there's something that is not okay. And when this rotation speed here doesn't follow the Keplerian motions, there's only one explanation for it, okay? In physical terms, since this is a physics question for us now, and the only explanation is that we need extra mass. Otherwise, we cannot make or we cannot expect the stuff there, the stars or the molecular clouds, to have such high velocities. Okay, that's the issue here. And this is actually when we discussed this about Milky Way in the Milky Way chapter, and we said, okay, in our galaxy, maybe there are some stuff that are faint, we cannot see them, and maybe that is this extra mass. Okay, we talked about some possible astrophysical objects. For example, we said maybe it's white dwarfs, and maybe it can be up to like 10% of this extra mass. Yes, okay, but it is not enough. Again, just for Milky Way. Then Okay, after just having this idea about this Milky Way, then we ask the next question. But is it something special to Milky Way or not? Then we said, no, this is what we see in all spiral galaxies, that we can have this kind of rotational curves. Okay, but again, this is a again, we have a distance issue here, okay? Because we want to resolve individual things in a other galaxy, but if it's too far away, we cannot do it. So this is a measurement we can do up to a certain distance in the universe, okay? But when we do it, when we look at nearby galaxies and do measure the velocities of things, okay? We measure the velocity, rotation speed is velocity, okay? And we put it here on this graph. Then we measure the distance here, okay? Then this is what we see actually, okay?